Hello and welcome back to this course. So last class we solved a few numericals understanding how the reversible cell potential varies with the temperature as well as the pressures, both for fuel cell as well as for electrolyzer. However, in all these examples we have taken Cp to be function of the temperature. Let's quickly understand what happens if we assume this heat capacity to be independent of temperature. So with that small numerical we will go ahead. So I am going to take the same numerical for a fuel cell. So for a hydrogen oxygen fuel cell, hydrogen and oxygen fuel cell, which involves this reaction, the conventional reaction, giving 1 mole of water. So I am going to take the same operating parameters, operating temperature is again 80 degrees Celsius and pressures, that is operating pressure of hydrogen is again let us say 3 atmospheres and operating pressure of air. So in the last numerical we had taken air to be oxidant. So let us continue with that. So 5 atmospheres. So these are my conditions. Now let us get the enthalpy terms and entropy terms. So we have H2 plus half O2, that gives H2O. Let us write the enthalpies and the entropies. Enthalpies and for both hydrogen and oxygen are 0. For water it is minus 286 or 285 also we can say. Let us take 286 kilojoules per mole on intrinsic basis, and we have entropy as 130.68, then oxygen is 205.14 and for water it is 69.91. This is in joules per mole per Kelvin. And let us also have or rather list out the Cp's. Now they are, since they are independent of temperatures, we have assumed Cp to be constant. So I have taken Cp remains constant in this case, just to examine its effect on the Nernst potential ultimately. So this will be 1.4 and this is 0.925 and this is in 4.186, right. So let us go ahead. So as we know, we have Et equals E naught plus entropy change by Nf. This is entropy of the reaction basically, T minus T naught, and we have entropy of the reaction which is entropy of the water minus entropy of the hydrogen plus half times entropy of the oxygen. So this is equation number 1. So let us calculate those entropies again. So entropy of water is standard entropy at STP plus integration 298 to 353 Cp by T dt. Now Cp is not function of temperature, that is what we have assumed here. So this simplifies our calculations and this comes 69.91 plus Cp is constant, it can be taken out of the integration. So we can write 4.186 integration of 1 by T dt. This is again 298 by 353. So this is 69.91 plus 4.186 ln of T, 298 to 353. So this is 69.91 plus 4.186 ln of 353 by 298. So, that comes close to 69.91 plus 0.169. So, that is 70.61 joules per mole per Kelvin. So, this is my entropy of water at STP, entropy of water at 80 degrees Celsius. Let us go ahead find out the entropies of the other species. So, let us go ahead with entropy of oxygen. So, that is entropy of oxygen at STP plus integration Cp by T dt. This function remains the same, only Cp will be varying for respective species. This is 298 to 353. Entropy of oxygen at STP is 205.14. So, that is, and Cp is I think 0.925. Yeah, Cp is oxygen is 0.925. That is constant, that will come out. So, this is again integration of 1 over T dt, 298 to 353, and this is 205.14 plus 0.925. This is ln of T over this temperature difference. It is the same thing again. So, if we solve this up, this comes 205.14 plus 0.925 ln of 353 by 298, and that is nothing but 205.14. So, this comes close to 205.29 joules per mole per Kelvin. So, this is entropy of oxygen. Let us go ahead and find out the entropy of hydrogen. Entropy of hydrogen is entropy of hydrogen at STP plus integration. I am going to take Cp out, and this is T naught to T 1 by T dt. So, this is entropy of hydrogen is 130.68 plus Cp is 1.4, integration of 298 to 353 1 by T dt. So, this is 130.68 plus 1.4 times ln of T again over 298 to 353. So, this is 130.68 plus 1.4 times ln of 353 by 298. So, this comes close to 130.91 joules per mole per Kelvin. This is entropy of hydrogen. So, now that we have found out all these entropies of the species, let us find out the entropy of the reaction. So, entropy of the reaction is delta S reaction, which is entropy of products minus entropy of the reactants, which we have already written. So, entropy of products is what is water, which is 70.61 minus 130.91 bracket. This is for hydrogen. For oxygen it is plus 205.29 by 2. So, let us solve this. This comes close to minus 162.94 joules per mole per Kelvin. So, this is the entropy of the reaction. Minus sign, as we have already discussed, minus sign indicates there is a the entropy decrease after the reaction has been processed, which means H2 plus half O2 giving H2O. So, that means H2 plus half O2 that is giving H2O. So, we have less chaos in the system, that is 1.5 mole, that is 1.5 mole of, and the reactant species have been converted into 1 mole of water, which is in liquid phase. If we assume this water into liquid phase, so that means 1.5 mole, is converted into 1 mole of liquid phase. As the gaseous products have been decreased after the reaction, the entropy will be decreased or is likely to decrease. So, that is what we have seen earlier as well. So, that is why there is a negative sign. So, let us go ahead and find out ET. ET is basically E naught plus entropy of the reaction by NF times temperature difference. E naught, as we all know, for the hydrogen oxygen fuel cell at STP, it is 1.23 volt. So, I can make a quick calculations here. So, we have E naught is delta G naught by NF and delta G minus delta G naught by NF. So, minus will remain same. Delta G naught for the hydrogen oxygen fuel cell is minus 237,000 joules per mole and N is 2, F is 96,485. So, this comes close to 1.228 volt, or we can write as 1.23 volt. So, this is a plus quantity, this minus becomes plus. So, plus 1.23. So, that is my E naught at STP. Entropy is minus 162.94 by 2 times 96,485 times temperature difference, that is 353 minus 298. Okay. So, how much is that ET? ET comes close to 1.18 volt. ET comes close to 1.18 volt. So, let us go ahead and find out the En. So, En, as we know, it is ET minus RT by NF ln of products, that is activity of water divided by activity of hydrogen times activity of oxygen raised to half. So, we know activity of water is 1 and what activity of hydrogen is the partial pressure of hydrogen by standard pressure. So, in this numerical the pressure is 3 atmospheres. So, 3 by 1 as, and activity of oxygen is the partial pressure of oxygen by standard pressure. So, there is an air that we have supplied to the cell. So, partial pressure is, and it is at 5 bar, 5 atmospheres. So, 5 times 0.21 divided by 1. So, this comes close to 1 and that is an activity. So, we let us substitute here. ET is 1.18 volt minus R is 8.314, temperature, operating temperature is 353 divided by 2 times F is Faraday's constant is 96,485 ln of activity 1 by activity of hydrogen is 3 times activity of oxygen is also sort of 1, close to 1 raised to half. So, if we solve this, this comes close to 1.19 volt. So, this is activity of hydrogen is activity of oxygen is little over 1. So, that is 1.05 actually. So, this should be 1.05 and that is why this term does not get cancelled out and it adds a little to this equation, and that is how we can get En as 1.19 volt if the fuel cell is operating at 80 degrees and pressures are 3 atmosphere and 5 atmosphere, and if you have supplied hydrogen and air. So, if you supply oxygen, the pressure will be the absolute pressure at which the oxygen is supplied. So, in this case we need not take into account the partial pressure of the oxygen as it will be 1, and then if we supply, let us say 5, if we supply oxygen at 5 atmospheres, then the activity of oxygen will be 5. So, the entire equation will again be changed and we will get a new Nernst potential. So, if you look at these expressions, we can understand that there is not much change in the Nernst potential that we can observe if we assume Cp to be constant or independent of the temperature. However, for precise results, we should take into account the heat capacity as a function of the temperature. So, with that we will move ahead. Let us try to understand the characteristic curve and the different losses. So, let us start with a new section or new heading, fuel cell characteristic curve, or it is also called as IV curve. Right. So, let us draw two verticals. This is my potential vertical, this is denoted by E, unit is volt, and this is my energy vertical. And this has unit kilojoules per mole. Okay. So, if we remember or if we recollect, let us take our standard hydrogen oxygen reaction. The enthalpy of this reaction, delta H of this reaction is minus 286 kilojoules, that is the total enthalpy. I can write it on intrinsic basis at STP, and is minus 286 kilojoules per mole. So, if I start with the maximum energy content, which is minus 286, or let me use the different colors. So, this is my potential curve, and let us say this is my energy curve, energy vertical. So, this is my maximum enthalpy, maximum energy content as minus 286 kilojoules per mole. If I convert this into respective potential, this we know how we can convert or rather play in between energy and potential verticals, we already aware of that. So, if we want to find out reversible potential or potential, we have to divide the energy term by Nf. So, Nf is a, right, as we have discussed this before, is acts like a barrier, acts like a carrier between the energy and the potential vertical. So, if I divide this 286 kilojoules of energy by Nf for this reaction, I get corresponding potential as, so roughly 1.48 volt, okay, and this potential is called as, or it is denoted by ETN, which is called as thermoneutral potential. This is which is close to 1.48 volt for hydrogen oxygen reaction. So, this is my first step, draw a line. So, 286 corresponds to 1.48 volt, which is thermoneutral potential. Then I have one slight drop here. This drop in the energy is due to the loss due to entropy, or I can write entropy loss. So, enthalpy is converted in, or if we subtract the entropy loss, we are left with the Gibbs free energy. So, Gibbs free energy at STP is roughly close to minus 237 kilojoules per mole. So, this corresponds to, as we know, this is your reversible cell potential, which is 1.23 volt. Then, since fuel cells are typically operated at pressures and temperature different than that of the STP, so there is a loss in the energy due to the deviation from STP. So, let me write this up. So, deviation from standard temperature and pressure conditions. So, as we have seen earlier, fuel cells typically operate at 80 degrees, 70 degrees Celsius at or 3 bar or 5 bar pressures. So, these terms or these operating terms are very different from standard temperature and pressure conditions, that is 1 atmosphere and 298 Kelvin. So, since we deviate from these STP conditions, there is a loss, and that basically drops the potential, and that potential is we normally denoted by Nernst potential. So, we need to calculate what could be the reversible potential when the cells are operated at typical operating conditions. So, this is the Nernst potential. Further, there is one more loss that pops up, which is nothing but loss due to fuel crossover. So, what happens is basically, as I will point this up here. So, we have this fuel cell, this is your electrolyte, this is my anode and cathode. So, whenever hydrogen is supplied, so instead of oxidizing at anode, that is H2 giving 2H plus 2 electrons, this reaction instead of occurring at anode, this hydrogen basically slips through this electrolyte. So, this is hydrogen as a pure molecule, it diffuses through this electrolyte and gets oxidized at the cathode. So, this is a very unfavorable condition, and that should be avoided. Depends a lot different parameters such as the thickness of the electrolyte, and which we will discuss as we proceed. So, this loss is basically loss in the fuel as it crosses the electrolyte and reaches the cathode. So, this loss is called as loss due to fuel crossover, because hydrogens are fuel here, and this can be minimized to some extent. It can be it can be completely minimized to 0 value when if we increase the thickness of the electrolyte. So, theoretically, if you have infinite thickness of the electrolyte, or if we have considerable thickness of the electrolyte, we can completely nullify this crossover loss. However, in practice, as we proceed, if we increase the thickness of the electrolyte, it will also incur more losses in the ohmic zone, which we will come to see now. So, these are the losses, where different losses that take place, and this is where finally we get to see the open circuit potential or voltage, open circuit voltage, which is also written as OCV. So, OCV for hydrogen oxygen fuel cell typically is around 1 volt, sometimes a little over 1 volt. So, this is what we will get to see if we connect the terminals with the multimeter. This is what we are expected to see, and that is open circuit potential when there is no current flowing in the circuit, external circuit. So, if I now start to draw the curve, so my fuel cell curve looks something like this. Okay. So, why this curve looks like this? Because there are 3 main losses that take place in a fuel cell. So, let us underline those losses. So, there are 3 zones basically. This is 1, this is 2nd, and this is 3rd. So, this is the first zone called as activation zone. And the loss that takes place, or rather dominates in this first zone, is your activation loss. Okay. So, this is the loss that takes place in the first zone. Second is your ohmic zone, this is ohmic zone, and the loss that dominates in the second zone is your ohmic loss. Third is your mass transfer zone, and the same loss takes place, or rather same loss dominates in the third zone. So, let me write it as mass transfer loss. So, these three losses basically incur in the system as and when we start drawing current in the circuit from the circuit. So, as and when we draw more and more current, more of these losses get added and we end up having such kind of characteristic curve for a fuel cell. So, how we can tune this curve so that we can get maximum current from the cell depends on what materials are used in a fuel cell. So, activation loss, as we will proceed, we will understand that activation loss is typically for or with respect to the catalyst that we are using. Ohmic loss is predominantly governed by the electrolyte resistance to the flow of ions as well as the other losses, and the mass transfer loss typically arises due to the ability of the gases to flow and reach the catalyst layer. So, that is how these three losses come and play a very big role. So, the efforts are always basically to minimize these three losses so that this characteristic curve remains as horizontal as possible. So, theoretically we should have curves to look something like this, which in other words we should be able to draw infinite amount of current for negligible loss or change in the potential, but that does not happen in reality. In reality, we have a similar kind of performance curve that we can see for the potential as and when we draw the current. So, these losses, as we will proceed, we will understand that these losses play a very important role in shaping this fuel cell curve, and this is what we will see in the upcoming classes. With that, thank you.